Hi! Let's dive in. The plan is to drive 8 rows of 8 LEDs each, to display letters, designs, or random patterns, to have a simple matrix in the background for my daily photo project. The easiest way to do so is to connect the LEDs as it's shown on this whiteboard. All the anodes, the positive terminals, of each column's LEDs connected to the same terminal to the voltage supply, and all the cathodes, the negative terminals, of each row's LEDs connected to a switch, going to ground. To turn an LED on, its anode must be put higher than its cathode. The current limiting resistors are necessary, otherwise the LEDs will burn, since the voltage provided is 5 volts. If we turn 2 switches on at the same time, more LEDs on the same column would turn on. And that might not be what we want. So the idea is to switch one row at a time, but do it very quickly, since our eyes and brain cannot process such a fast flicker. To drive the anodes for the columns, I'm using an 8-bit shift register. Its pinout is like this. We are going to drive the data pin, the clock pin, the strobe pin, and the output enable pin with an Arduino Nano. The outputs are then connected to the anodes of the LEDs through the resistors. Let's say we want to write the row in blue here. For each rising edge of the clock, low to high, the value on the data pin is written in the bit number 1 of the register, and each value already written in the other bits are shifted to the bit on the right. After all the bits are written, we pull the strobe pin high to save the bits on the corresponding latches for the output. Then we enable the outputs and the switch, in our case an N-channel MOSFET, to turn on the LEDs of one row. Then a new cycle will start. The circuit is planned. Let's quickly see my soldering process. Now the code I wrote for the Arduino Nano. I defined the pin labels, assigned a few variables, and the matrices I want to display on the LEDs. In the setup there is the code that will be run once, at startup. The input or output mode of each pin are defined, the timer 0 and the interrupts registers are set. The main loop is quite short. It simply calls the function writeSR, defined later, to drive the data pin of the shift register. Then it turns the row on and then off. The interrupt service routine, ISR, of the timer 0 is used to drive the clock pin of the shift register, as well as the MOSFET of each row. The ISR of the PC int 0 is used to deal with an interrupt on change of the button pin, to go through the matrices. Then the function writeSR is the one called by the main loop. Each row is sent to the shift register with the method explained earlier. As we can see on the oscilloscope, the code works as expected. In yellow there is the clock sequence, with its on time of 4 microseconds, and here in blue the strobe pulses. Zooming out, the clock pulses are still in yellow, and in blue the pulse for the MOSFET of a single row, repeating every 8 data cycles. It's clear by now that the LEDs are going to be turned on for roughly 12% of the time, so they won't be too bright. And here we can see the output enable pin going high after each data cycle. The circuit looks good enough. Now for another time-lapse of me figuring out how to make an enclosure for the board. It looks alright, it just needs a bigger button, so I designed it in FreeCAD and printed it in orange PLA. And I think it's too dim. Maybe the diffusion screen blocks too much, and it might be good to have some higher contrast. Let's paint it black. I could also print a translucent screen. Indeed, it looks a bit better now. New button as well, in grey silver. Will it work now? Still quite dim, but I think it's a bit better. Definitely the low duty cycle is to blame, as well as the fact that the matrix isn't exactly the protagonist of the photo. Anyway, here is an example of the result. Before leaving, just a quick demonstration of what it would look like in slow motion. This was my first time making a video like this, so I hope you liked it. Thank you so much for watching.